Concentration calculations part 2. This is looking specifically at KSP. So KSP is KEQ, but specifically looking at solubility. So remember that all of these are experimentally derived. So KEQ values, KSP values, any K something is a specific KEQ. So we'll be seeing these later on when we look at acids and bases. Acids have a Ka, bases have a Kb. So it's something that you'll see over and over again. First new one is KSP. So remember that the limit of solubility is experimentally derived, and it's also very temperature specific. You know that if I change the temperature, I can increase the solubility or decrease the solubility of a compound depending on what I'm looking at. So here's an example. The KSP of barium carbonate is 5.1 times 10 to the negative 9th. Calculate the solubility of barium carbonate. We always write our equation as the dissolving, the dissociation of my ionic compound. So no matter what, whenever I use KSP, I always write it as if I have my compound dissolving and I'm creating aqueous ions. So my KSP value, because this is a solid, only contains the ions to their coefficient exponent. So these all have a coefficient of 1, so I don't have any exponents here. So my KSP value is the concentration of my barium ion times the carbonate ion. It's important that you always put the ions in there. It's one of those dotting your I's and crossing your T's thing. If you don't have that in there, you'll get points off. And that's equal to 5.1 times 10 to the negative 9th. When this dissociates, I create barium and carbonate ions in a 1-to-1 proportion. So at equilibrium, my barium ion concentration will equal my carbonate ion concentration, and I can just call that X. That X, because of my 1-to-1-to-1 ratio, also is the number of moles of barium carbonate that we're able to dissociate per liter of solution. So even though I'm thinking of this as a solid, I can also think of it in terms of the limit of my solubility. So X squared, because I'm multiplying these two, is equal to 5.1 times 10 to the negative 9th. And if I solve for X, it becomes 7.14 times 10 to the negative 5th molar. That again is the maximum limit of moles of barium carbonate that I can dissolve in per liter of solution. So if I simply multiply this by the molar mass of barium carbonate, which I have here, 137 plus 12 plus 16 times 3, I find that I can put in 1.4 times 10 to the negative 2nd grams per liter of solution. So under these circumstances, the maximum number of grams that will dissolve per liter of solution of barium carbonate is 1.4 times 10 to the negative 2nd grams. It's a very, very small number, right? Approaching the limit of our balances. So just a sprinkle of it in a whole liter of solution is all that can dissolve in a liter of solution. Here's another example. I have lead 2 chloride, and the KSP is 1.6 times 10 to the negative 5th. It's a little higher. So calculate the solubility of lead 2 chloride. This is a different case because for every mole of lead 2 chloride that dissociates, I create 1 mole of lead ions, plus 2 ions, and 2 moles of chloride ions, right? As I dissociate that, I create 2 moles of chloride ions and 1 mole of lead 2 ions, so these have to reflect my coefficients. Which means that my KSP expression will be the lead ion concentration times the chloride ion concentration squared. So remember, this coefficient occurs twice, not just in the stoichiometry here, but it occurs again in the exponent right here. So then I plug in my X and 2X values here, remembering that this squared applies to the coefficient as well as to my variable. And I end up with 4X cubed is equal to my 1.6 times 10 to the negative 5th. I solve for my X, so I divide both sides by 4, then I take the cube root, and I find out that 1.58 times 10 to the negative 2nd moles per liter is the limit of the number of moles of lead 2 chloride that will dissolve. So then I place this, and I multiply it by its molar mass, and I get 4.41 grams per liter. So the molar mass is greater, which is one reason why I can bit more grams per liter of lead-2 chloride. But the main reason why I have a difference between 1.4 times 10 to the negative second grams per liter and 4.41 grams per liter here has to do with my KSP, right? So here, my KSP value is 5.1 times 10 to the negative ninth, and here it's 1.6 times 10 to the negative fifth, a full 10,000 times greater than here than it is here, right? Remember these negative exponents. So the general strategy for these is, again, you write the KSP expression, and you solve for X, which is going to be the moles of ionic compound, my reactant, that can dissolve in solution, right? So this and this. And then I multiply by the molar mass to figure out how many grams per liter of my ionic compound will be dissolved in water. So again, writing down the KSP expression, solving for X, and then multiplying that by the molar mass of my original ionic compound.